Welcome to another lecture for Auto 202. We're going to cover chapter 22 today, which is going to be going over fuel injection components. Now, when we're looking at fuel injection, I want to make sure that it's understood it's low pressure fuel injection. So when we're looking at this, we're looking at throttle body and port fuel injection. We will have a separate lecture, chapter 23, about direct injected engines, specifically injection into the combustion chamber itself. For this lecture, though, however, we're going to be talking about electronic fuel injection that is involved with spraying fuel directly into the intake valve. So what's photoed here is not what we're discussing. That is going to be direct injection. So I do want to make sure that's understood because a big deal with that is the amount of pressure that's being used for either one. So when we talk about electronic fuel injection, we're looking at electronically controlled fuel injectors that are going to be metering fuel into the intake manifold or pre-combustion chamber. This is going to be taking fuel from the storage tank, moving it up through a set of feed lines into a pressurized rail, and then out to the fuel injectors that will then spray and allow that fuel to atomize. Now, there's a couple things that we're going to have going on with our fuel injection system. The first and foremost is we have to have some sort of control. Unlike a carbureted engine, which is going to be using mechanical means to atomize the fuel and air mixture, we are going to be utilizing the computer via a series of input sensors to be able to spray the fuel injectors at the correct time. Now, there are going to be some programming differences between the different ways that we can fire these injectors, and we'll talk about that in the later slides. But ultimately, when it comes down to how the system is going to operate, is the PCM is going to control pulsing, or basically turning the injector on and off, and at which time it's able to do that. PCM will also be in control atypically of a fuel pump control. That will involve allowing an electric fuel pump to feed moderate pressure to the fuel rail and pressurize that so that the injectors have a constant feed. And when I say moderate fuel pressure, we're looking at anywhere between 30 to about 60 psi on average for a fuel injection system. Now, the PCM is going to have a couple different control options in terms of controlling that fuel delivery. There will be a quick, it's usually 5-ish seconds, pulse of the fuel pump to basically prime the fuel line so that when the vehicle is started, it can start quickly and stay maintained starting. What often happens, especially on return style fuel systems, is when the engine is shut off, the fuel will naturally want to drain back to the fuel tank because the fuel tank is in the rear of the vehicle and usually lower than the fuel rails. So that, gravity naturally brings it back and depletes any positive pressure that would be in the fuel rails or fuel lines, and therefore we need to prime it. Deadheaded systems can hold pressure for a little bit longer, especially a deadhead system or returnless style system is how the book talks about it, that has a pressure diode valve that keeps everything pressurized. But it is going to be, there's going to be multiple components that are going to be controlling the aspect of this. Now, when we're looking at the actual fuel operation, the computer is going to control when the pump is going to turn on and off, usually by sending power to a coil inside of a relay, and the relay switching over and sending 12 volts or battery voltage to the pump. And then it's going to control the pulse width or the on and off functionality of the fuel injector. What it's not going to control is going to be the actual fuel pressure. The fuel pressure will be controlled via a fuel pressure regulator. This fuel pressure regulator we'll get into on where it can be located and its functionality, but that's typically going to still be a mechanical means. We do have methods in which we can regulate fuel volume, but not fuel pressure. The fuel pressure will be a mechanical means. Our first forms of fuel injection came in the form of throttle body injection. This is kind of emulating what we already kind of had as existing technology for fuel mixture, and that would be a carburetor. And so what we're having is we are having anywhere between one, two, or four fuel injectors mounted inside of a throttle body, and they would spray that fuel into the incoming intake port. Now, there's a couple different methods at which we can do this. There is going to be the spray nozzle injectors that will spray above the throttle blades. This is very typical of what you see right here for the GM TBIs. These are dumb reliable. I've installed these as an aftermarket. I shouldn't even say aftermarket, as a different brand style of fuel injection on a couple vehicles, and they're really, really reliable in how they operate and how they function. Or we can have it more traditional style, which is going to be similar to port fuel injection, where we'll have individual needle and pintle injectors that are going to be mounted on fuel rails after the throttle blade. But when we're looking at this early design, throttle body injection is very simple. We don't have to really do any major changes to the engine's design in terms of our induction system. We're going to have a similar intake manifold. In fact, I converted my 1964 Ford to fuel injection. I didn't have to do anything to the intake manifold. I literally was able to take the carburetor off and put the throttle body on. I had to have sensor inputs, but in terms of like designing or remanufacturing how the intake manifold was shaped, it didn't matter. Now I have noticed I have made a change to my truck. When I first built the motor, I was running a dual plane intake manifold that's very similar to a what most street driven carbureted engines are going to require for a V8. Now, what a dual plane intake manifold is there's two segregated paths of incoming air after the carburetor, and the idea is each individual pathway would allow for scavenging pulses to benefit drawing in that fuel and air mixture from the cam overlap. However, I have found, and as well as many other people that are much more educated than I am, that throttle body injection that is running at higher pressure, so higher pressure than like what this GM system is running. The GM system's running like 30-ish psi, but I'm running close to 50 psi on my truck, and it's running in a batch injector pulse. It's better to have a single plane intake manifold, or otherwise the intake plenum is all open, and so all eight ports are equally exposed and equally able to get flow. What it basically is doing is it's eliminating the frequency that can happen with a dual plane manifold. So that was actually an upgrade that I just recently did to my truck, and it kind of woke that up, and it's been pretty big benefit. Now, port fuel injection is going to be the other design, and port fuel injection is where we're going to actually stick that fuel injector a couple inches from the intake manifold, or sorry, from the intake valve in the intake manifold. Excuse me, I'm trying to talk too fast. And that is a much more efficient design than our throttle body injection. The idea is this injector is going to be spraying fuel with just enough time to atomize and basically mix with the incoming air and get into the combustion chamber via the open intake valve. Now, the benefit to this is depending on how we have the injectors timed, whether or not it's a sequential or a non-sequential design, we're able to spray just the right amount of fuel. We also don't have any fuel deposits that are going to be stuck to the intake manifold, although we will have that in cases where we have an open plenum and there will be some reverberation pressure going back the other way in the intake manifold to the next cylinder that is going down on the intake stroke. So what that means is when the piston is starting to drop down on the intake stroke, it's drawing intake gases, so the intake air and gasoline, through that port. And so some of the gas that did not get sprayed or was left over from the fuel injector on the prior intake stroke can get mixed with that. So we can have some fuel deposits when it does come to coating the intake manifold. Now, there's going to be a couple methods in which we are actually programming or getting the prediction on how much duty cycle or pulse width we should have for our fuel injector. We've talked about these in the past. It's going to be speed density and it's going to be mass airflow. Now, when we look at speed density is going to be looking at the lack of pressure inside of the manifold, again, post throttle body. So after the throttle body, when we have that sealed intake manifold, we're looking at that pressure. So we're going to be using a map sensor where we're not so much worried about the airflow. So on speed density vehicles, the PCM is going to calculate the amount of air needed for all of the cylinders based off of engine RPM, as well as load, which is going to be calculated through throttle position, and then average that based off of the different temperatures that the engine is seeing in terms of the coolant temp, the inlet air temp, and then we're able to make fine-tune adjustments after the oxygen sensors have read and given what corrections, or given the data so the PCM can determine what correction is going to be needed. And then that can go in, its adaptive fuel memory so that the vehicle can be more predictive on how it's going to operate. Now, for this speed density equation vehicle to work, we're going to have to make sure that we are also taking a barometric reading. So when we get that pulse width calculation, we're taking the MAP, or the manifold absolute pressure data, the baro, which is going to be the ambient barometric pressure, and then we're going to take the RPM over the maximum RPM. So the RPM we're operating at, and then the red line at which we can operate the motor at, which isn't always where motors live, but we want to make sure that we're supplying enough fuel at those higher RPMs. If we don't supply enough fuel at those higher RPMs, we run the risk of pre-detonation, and therefore we could run higher temperatures in the combustion chamber, which is going to be doing direct damage to the engine. Pre-detonation, again, is one of the things that we're trying to avoid, otherwise known as knock. If we're getting into where we have a pre-ignition knock, you will start to do damage to internal components of the engine, atypically the piston because it's weakest because it's made of aluminum. Now, mass airflow was the earliest method in which we were able to calculate injector pulse width. Basically, it's just taking the amount of airflow or calculated airflow being drawn into the engine and dividing that by the engine's RPM or operational RPM. Now, with mass airflow, we don't have to worry about the maximum RPM because airflow is going to be maxed out, or the amount of air being drawn in prior to us getting to redline, because as we increase in RPM, we're going to be increasing the amount of draw on the engine, or the amount of airflow going in to our manifold absolute pressure sensors or speed density equation. We're going to lose that negative pressure inside of the intake manifold because the throttle body will be open, and therefore we will have more equalization of the pressure between ambient and manifold pressure. But in a mass airflow system, we're just looking at how much air volume is going through the inlet system. So we're going to be taking an average of the ambient temperature and then using a hot wire system or a trapdoor system. So like the very early system that I have photoed here, that would be on the left of the chart, that is going to be basically a trapdoor system. Inside of that, it's going to have a trapdoor that will move very easily against any type of airflow and operate off of that. So it's only going to have so much room that it can go in. But the other style, the different hot wire style, or hot film is the other style one, they will be using an ambient temperature sensor so that it can predictively figure out how much the hot wire and or hot film is losing temperature, and therefore it can calculate that airflow. Now, the downside of these systems is obviously if there is any junk or contamination of that hot film or hot wire, it won't function correctly. Quite honestly, the trapdoor systems actually work pretty well as long as they're working correctly. I have had one horror story with one of these, with doing some dyno testing. We were racing spec 944 class cars, which if you're familiar with spec Miata, it's similar, just with Porsche 944s. Honestly, kind of the better racing. They're so Spec Miata is really great, right? Miatas are fantastic, but Spec 944, it's a transaxled front engine, rear wheel drive vehicle. They're 2.4 liter naturally aspirated four cylinder engines that are single overhead cam. And the engines actually perform pretty well. But anytime you're racing a spec class where you're basically racing to the rule book and everyone's following the same rules, so it's really kind of, as if the driver has exceedingly better talent than other drivers, that's who's going to win. We try to exploit that and try to give ourselves a mechanical advantage. So one of the things that we were playing with on the dyno was we were playing with actually maxing out that mass airflow. So the rules stated that we had to have, factory Porsche management system. So we had to run the factory computer. We couldn't run an overtune or anything along those lines, but it didn't say we couldn't mess with it, or at least, it'd be, hard pressed for a scrutineer to actually look at that. So one of the things that we messed with was we messed with taking apart the mass airflow trap door and permanently keeping it wide open. The thought process was is if we always tell the engine that it has maximum airflow, it will provide more fuel, will be a little bit richer fuel mixture, which then we can ultimately make a little bit more power. Thankfully, the person that made this mistake was the owner of the shop, because we all would have, we very much feared him, and we probably would have felt we were going to lose our jobs and our lives at that point. But we were running the car on the dyno after he'd made this modification. One of the unique things with 944 naturally aspirated cars, they have a metal intake manifold. It's cast aluminum, and it's got these really long trumpeted runners for really good low end or high RPM operation, while also allowing for a little bit of low end torque with how they were angled. But we could hear, so we start to bring it up on RPM, and we're going up, we're going up, we're going up, we're going up, and you can hear dink, 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 boom. And what had happened was one of the bolts came loose because we hadn't used Loctite, and we could hear it ricochet down the intake manifold, get past the intake valve, and then go into the it was cylinder number 4. Typically, whenever you get any type of debris in the cylinders, it always goes to the back cylinders. That's because the engine's always at an angle downward, so your front cylinders are higher up than your back cylinders, so gravity kind of draws it that direction. And yeah, we absolutely grenaded cylinder number 4 piston, like blew it into a bajillion pieces. And then, like, obviously, because that happened at higher RPM, so this was at probably pushing 6,000 RPM. The connecting rod had no more support, the small end of the connecting rod, and it buried itself into the cylinder wall, and the engine was gone. There was nothing we could do to save it. But other than that one, horror story and having them, get dirty on a fairly regular basis, mass airflow systems work pretty well. Now, when we look at going back to that throttle body injection, we will the firing of our fuel injectors or non-synchronize them. Most will be non-synchronized. When we synchronize this, we're going to try to pulse the injectors alternatively, and that will kind of be going along with our dual plane intake manifold. So we have that Chevy Silverado, that 1989 Silverado. It is a TBI fuel injected engine that is in that, and it does have a dual plane intake manifold, so that we can have better drivability at low end torque, because it's a pickup truck that was meant for towing. It will pulse the fuel injectors, and it is a synchronized pulse of each injectors, and you can actually hear it. These old GM TBI systems, you could hear the dunk 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 dunk, dunk, and it sounded like they were kind of dancing. Especially if you have like a completely stock exhaust, if you have the hood up and the air cleaner off, it sounds like they're dancing because they're fully synchronized. However, as we found that there's better power output and better torque output with a open plane or a single plane intake manifold, we went to non-synchronized, where it basically pulses all the injectors at a given time, to allow for the maximum amount of fuel to go in. Now, the disadvantage to that is we're very inefficient on fuel, because we are basically dumping all of it in as much as we possibly can for the throttle load, obviously. When we started to see manufacturers paying more attention to fuel economy, as gas prices started to increase, we started to go as a more efficient design. And by far, port fuel injection is way, way, way more of a efficient design versus our throttle body injection. Brings the fuel injector closer to the intake or into the intake valve. I keep getting that messed up. I'm sorry. And it allows for the maximum amount of fueling for the distributing the fuel the most efficient. So what it like, basically is looking is between 2 and 3 inches or 70 and 110 millimeters away from the intake valve. We are going to have a fuel injector placed, and it will spray fuel with the incoming air being drawn into the intake down during the intake stroke and down into the engine at that point. Now, we will have the fuel injector operate a little bit different typically. We're going to have it act more as a solenoid in this case versus the throttle body injection. But what we're going to be looking at is we're going to have that solenoid energize once the PCM gives the injector ground. It completes the circuit, opens the pintle off of the needle, and that is going to spray fuel in. Now, when we say duty cycle of fuel injector, it's the period of time at which the injector is on, not how much fuel it sprays. Normally, when we look at a fuel injector rating, we're rating them in pounds, and that's pounds of fuel per hour. And the higher the number, the more fuel flow you're going to get out of them. So, like one of the things that you can do, I've never done it personally because it kind of wigs me out, is denozzling fuel injectors. So if you have a vehicle that you're trying to gain more power from, let's say you turbocharged or supercharged a engine that does not have fuel injectors that are readily available on the aftermarket that are higher pound rating, you would take the stock injectors out and you would take the usually there is a shroud covering the needle in the pintle, and that would unshroud or open up the fuel injectors. It's typically the phrase for it is uncapping fuel injectors. Like I said, that's getting too much where like the injector could spit its guts out, and those are all going to be hardened parts that are not going to bode well for the internal combustion components inside of that engine. But this kind of gives you an idea of what's going on inside of the fuel injector. So you're going to have fuel going in through the inlet. That will then have basically a gated stop at the plunger. When the coil windings move, that opens that valve up, and that will then allow for fuel to go around into the needle valve. And with that pintle open, it will then inject it. Now, fuel injectors can have a variety of different patterns at which they can spray. Typically, they're going to be aimed and spraying in a cross pattern or a Y pattern to go around the tulip stem of the valve. If it's sprayed straight at the valve, it hit the valve stem and then come backwards and reverberate through, and it wouldn't actually get a situation where it would mix with the air and you wouldn't have any power. So instead, we're trying to spray it around that stem so that we can have it operate in a manner that we could get fuel into the cylinder. Now, one of the ways that we can have our port fuel injector fire is what's known as a group fire. It can be known as gang fire. I've never heard of that except for the publisher saying that. I've always known it as batch fire. And why I've heard it as batch fire is you're going to have batch one, batch two, basically bank one, bank two, and you have a batch of fuel injectors that are going to fire at any particular time. And typically what we're going to do is if we're looking at like a V8, for instance, we're going to have multiple cylinders at top dead center at any one time or close to there, around about. We're going to have cylinders that are partnered or paired in that one will be at exhaust top dead center, one will be at compression or power stroke top dead center, and one will be on intake and one will be on exhaust. So what we're going to try to do is we're going to try to match the cylinders that are drawing in air at similar times so that we can maximize the amount of fuel getting into the cylinder. Now with batch fire fuel injection, it's kind of the down and simple way of doing it, and that it doesn't take a lot of programming, and it's not as sophisticated. I guess that's the better term to put it, because it's kind of haphazardly spraying fuel in. It allows for the engine to basically operate, but not operate in the most fuel efficient manner. We will have double fire injectors, and this is where we're going to have two pulses per the four-stroke cycle. Now, why we're having those two pulses is it's way easier to engineer it that way. And it allows for the fuel injection system to be adjusted a little bit faster to fuel air ratios. And typically the way that it's going to work is it's going to allow for those instances where we have the exhaust stroke coming, or the pistons coming up. We're going to spray fuel and it's going to be pushed back into the manifold and then used at a different time. Now, sequential fuel injection is the most optimal way to fire the fuel injectors. This is going along with the engine timing. The PCM is going to be paying particular attention to the crankshaft position and the camshaft position, or camshafts position, if it's multiple camshafts, and that is going to allow for the maximum amount of performance to be had from these systems. We're going to match when the cylinder is about to open the intake valve to start firing the fuel injector, so that right at the intake stroke, when the intake valve is open, we are spraying fuel and there's already a small amount. Typically, it's going to be a little bit more advanced of the intake valve opening, so that it can start to do the tumble swirl. And it's going to go down into the combustion chamber, and we just have to spray the amount that's necessary to meet that stoichiometric 14.7 to 1 ratio. Now, the important thing to remember with this type system is the PCM does have to have the computing power to be able to pay attention to all of the cylinders. So if we have a V8, for instance, we're paying attention to firing the injector right at the point that it should be when we're at the intake stroke, and that intake stroke is going to be different for all 8 cylinders in that 720 revolutions of our crankshaft. So our camshaft timing is going to be really important for our sequential fuel injection design. Now, we brought up regulating the fuel, and now regulating the fuel is going to be important because we're going to have the fuel volume need to increase with throttle load. So we're going to try to maintain the pressure while we're operating the engine. So how we're able to do that, but then also increase as pressure also decreases in the intake manifold or less vacuum, is we're going to do that through a pressure regulator. Now, the fuel pressure regulator can be located in a couple different areas of the fuel system and be a couple different type design. For the most part, what it's going to do is it's going to have a spring that is going to block off fuel going back to the tank or fuel going to the fuel rail. And when pressure exceeds and overcomes the spring pressure of the poppet valve, it will push down and allow fuel to go past. Once that happens, though, however, that high pressure that was pressing down on the poppet valve is going to go to a low pressure area of either the return line or waiting to go into the fuel rail, and therefore the pressure will decrease right above the poppet valve, closing it back. The spring pressure will close the valve off, and then we will start the process all over again. Now, these systems will allow for fuel pressure to be maintained, and when we have this system vacuum controlled as well, where we're taking a sample of the manifold vacuum to allow for it to ramp up more fuel pressure when needed when we're under full throttle and there is less manifold pressure. That allows then the engine to match what the performance that is being expected by the driver. Now, when we're looking at the fuel pressure regulator, we're usually using these on return style systems after the fuel rail. So we're completely pressurizing the fuel feed line, the fuel rails that feed into the injector or fuel rail if it's a single fuel rail, and then we're having a low pressure return after that. We can have this for both throttle body and port fuel injection. It really kind of just depends on what the OEM has designed for it. But effectively, the point is that the high pressure, or well, I shouldn't say high pressure because it's the only pressure. The pressurized fuel pump is going to pump the fuel through the system into the rail. After it goes out of the rail, with the injectors closed, then we can regulate the pressure down. And again, we're looking at anywhere between 30 to 50 psi of fuel pressure from these systems. So with these spring controlled fuel pressure regulators, when there is engine vacuum, the engine vacuum will pull on a diaphragm that reduces the spring pressure's outward force against restricting fuel to go back to the tank. So under that reduced pressure, for instance, if we have 20 inches of vacuum being applied to a 46 pound spring, we're able to have the vehicle idle and have the correct amount of fuel return because we don't need as much volume and as much pressure at that point with the operation of the engine being lower with that. We also can have diode valves and filters inside of these fuel pressure regulators. This is especially the case on systems that are going to be not return style. Although Subarus do run return style fuel systems with filters and dampeners at the fuel rail. There's kind of a lot going on some of these fuel rails for those Subarus, and that might be because the early fuel injections and fuel injectors on Subarus were side port or side feed, which was very popular amongst Japanese engines, which I'm glad they got rid of because they're super inefficient on fuel flow and they kind of are more work than they're worth when it comes to it. But internally, these fuel pressure regulators, they can have a screen and a filter. Now you will still have a fuel filter coming off of the pump or feeding before the pump. Ideally, you want a fuel filter before the pump and then after the pump. That way you can catch any debris going into the pump, and if the pump does fail, you can catch it before it goes to the rail or the injectors. But fuel pressure regulators are one of the things that do fail pretty consistently on fuel systems. When you have a fuel pressure regulator that is stuck in one direction or the other, usually they stick shut. You're going to have very low fuel pressure, if no fuel pressure whatsoever, when that's the case. Now, I brought up that these fuel pressure regulators are typically going to be vacuum biased, and this is going to allow for the engine vacuum to control the pressure regulator to ensure that the pressure drops is constant across the injectors at idle and is ramped up at higher RPMs. And again, this is going to be based off of a diaphragm that is getting a port or well, no, I take that back. It's going to be manifold vacuum pressure so that it is able to have a consistent draw to all the injectors. Now, what a lot of manufacturers have gone to is they have gone to returnless style systems, and it makes a lot of sense. The benefit to a return system is you're cooling all the fuel system components. You're cooling everything down because you're using anywhere between 60 and 80% of the fuel delivered to the engine. The other fuel that is sent back to the tank acts as basically a cooling system to bring that heat back to the tank. disperse it amongst the fuel that is waiting in the tank, and the process starts all over again. However, you do have to have additional plumbing and additional fixtures inside of the fuel tank, as well as the fuel rail, and so on and so forth. And the regulator has to be mounted externally. But in a returnless style system, what we can do is we can have a fuel pressure rail sensor that is going to be a pressure transducer that is going to detect how much fuel pressure is at the rail, and the PCM or engine controller can calculate exactly how much draw we can reduce or pulse the fuel pump at to maintain a constant fuel pressure. Now, the benefit to this is we're reducing components, which reduces ultimate cost, and we're simplifying the fuel supply system. But it doesn't have the benefit of it cooling everything down like it once did. So there is that little bit of a drawback, but the cost benefit, as well as the ability for the fuel system to be pretty consistent, is high. Now, we do have to have fuel dampeners installed on the fuel rail when this is the case, and that is because anytime we pulse width modulate anything, we can create a harmonic. And what we're not trying to do is we're not trying to send that harmonic to basically press the fuel back. So we're going to have a dampener that is going to allow for every time that pulse of fuel comes into the rail, it basically takes up that slack so that we have consistent pressure throughout that rail the entire time. Um, this can typically be found on the fuel tank or fuel pump in the fuel tank, but can be found on the rail as well. When it is on the fuel pump, typically what we're going to have is we're going to have it dampen the fuel pulses into what's known as a surge tank. And this is a good idea to have on any fuel system, is where you're feeding from a larger tank into a smaller tank. And that smaller tank, the goal is to always be full. So anytime you have a surge in power, you have proper fuel supply. So what this allows for is this allows for the fuel to be basically drawn into a basin that the electric fuel pump is always going to be submerged in. Therefore, it keeps the electric fuel pump cool, so it's not going to overheat because it's fully saturated in the gasoline. And it will allow for the system to be a single line type design. Now, our fuel injectors themselves, they're going to be a solenoid. We're going to have that copper winding coil pack around the pintle that is going to allow for the fuel to go into the injection portion. And that also allows for really fast operation and movement. When we're looking at fuel injectors themselves, they operate at a much faster rate than that of a carburetor would be able to, that's vacuum controlled. It also allows us to have a lot more control in terms of the computer can maximize the vehicle's performance and fuel efficiency by increasing the pulse width based off of the input data that it is getting live from the vehicle operation. I do want to make sure it's understood with this design that the electronic solenoid component of the fuel injector is completely separate. The fuel is going to be passing through a straight through a port that is only going to be blocked off by the pintle and the needle. When we have this type of system, it's very rare for it to come in contact with the coil. In fact, I've never heard of one. That being said, knock on wood, it's bound to happen at some point. But the system is pretty simple with how these injectors are going to work. Now, the spray pattern, again, is going to be a little bit unique in that it's going to go through and around the stem of our valve. One of the other things that we want to make sure that we're paying attention to is that our volume of the injectors is all going to be the same. Ideally, we're trying to atomize the fuel into the air so that we have that, rich mixture. When I say rich mixture, I should say a consistent mixture. That's probably a better term for our engine to operate correctly. But we also want to make sure that all the injectors are flowing the same. So it is a good idea if you've had any type of catastrophic engine failure, or if you have an engine with high mileage and you're suspect of drivability issues, you can send your injectors out for flow testing. I've done this a couple times. I cannot recommend it enough. There's a company called RC Fuel Injection that is in like Montclair or somewhere in LA County that very quickly can clean, test, and verify your fuel injectors. And I found that it's extremely helpful because what it allows you to know is that all the injectors are consistent. And we would do this with the time attack cars as well. So with the cars that we were running pretty high horsepower on, that we needed consistency with, we would buy a grouping of injectors and have them match balance them all so that we would have a stack of injectors that were going to work in a particular engine. Now, there is another design of fuel injection system that is really weird. This is called the central port injection system. And basically, this is one big fuel injector with little basically poppet ports or nozzles that go out to each system. Now, a bunch of manufacturers had these, Volkswagen, Mercedes, Audi, but domestically, General Motors is the one that had this, what's also known as a spider injection. And basically, we have our central fuel injector that's going to have a pressure regulator and then nozzles going out to each one. If you like these systems, that's good. I'm glad you like quirky things. They kind of suck. There's obviously drawbacks to having the fuel have to go through transfer tubes from the fuel injector, and you don't have the ability to properly time it when that's the case. Now let's talk about the different operations of a fuel injector. So we're going to have our starting or our cranking. This is going to allow for the fuel pump to pressurize the fuel rail, and it may pulse the injectors once. It's kind of similar to if you have a carbureted vehicle where you'll pump the throttle a couple times so that the vehicle will fire up on a cold start. It's kind of the same theory. It is one of those situations that the PCM has the ability, though, to look at ambient air temperature and coolant temperature to be able to determine if we need to have a richer open loop mixture than we otherwise would. Now, we also can have a clear flood mode. Engines, when they become flooded, they prevent the spark plugs on gasoline engines from being able to ignite the fuel and air mixture. So when we have really low engine RPM due to low battery, and we are having high airflow or high load, we will shut the injectors off entirely. Therefore, what we can do is we can be drawing air in and sending that air to be able basically to push out the overabundance of fuel into the exhaust so that we can clear it out. I showed you all when we did the relative compression test that we did a clear flood mode where you're basically holding the throttle all the way down and the brake all the way down while you're cranking it, turns the fuel injectors off, and it allows for the engine to basically clear any type of flood. Now, ideally, an engine is going to try to get to operating temperature as soon as possible so that we can go into closed loop operation. Closed loop operation is going to be modifying the pulse width of the fuel injectors based off of inputs from the oxygen sensors, when the oxygen sensors have come fully up to temp. Prior to that, though, when the engine is cold, we're going to be in what's known as open loop mode. And this is going to be the mode at which the engine is going to operate when we are at below operating temperature. And operating temperature can be different on every manufacturer. Minimum I've seen is 140 degrees, but we can see it upwards of 195, 190 degrees when that is the case. Engines tend to have less hydrocarbons emissions if they run on the hotter scale of the combustion process, and therefore you're less likely to produce that harmful emission gas. So we'll start to see operating temperatures on more modern vehicles be a little bit higher, sub 220 operating temperatures, but very much within that 200 to 210, 215 operating range, which does give me a little bit of anxiety as a mechanic because you're right on the verge of causing massive overheating. But when we're an open loop, we're only in that for a temporary amount of time. Ideally, the engine gets up to operating temperature as quick as possible because we're going to get the proper performance out of the engine, but also the proper fuel economy and reduced emissions. We'll also be looking at a mode of operation of enriching the fuel when we're accelerating. Now, this is something that gets tuned into the injectors. And basically, we're looking for certain throttle positions or percentages, and that will increase or give a longer pulse width, basically operating the fuel injector at a longer time for us to have the needed fuel for accelerating the engine and getting into like that passing gear or getting to its final speed. The last thing we're going to do is going to be, well, second to last thing I should say is going to be deceleration. And this is basically going to reduce our fuel being given to the injector so that we can naturally slow the vehicle down. What this allows for is this allows for the computer to have the ability to reduce the pulse width or shut the fuel injectors off entirely, and allows for the engine to basically decelerate. The very last stage is going to be the anti-dieseling mode. What dieseling is where there is enough manifold pressure that it can force the needle and pintle open on the fuel injector, basically overcoming the return spring pressure, and it will cause the engine to still run. Now it runs like dot 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 dot, and can backfire and be prevent potentially very damaging to the engine. But that is the last thing we're going to have on our injector mode, and that basically is going to allow it to shut off entirely. Usually when we shut off of an engine, we'll shut off the fuel pump and shut off the injectors, and that stops the combustion process from happening. We'll usually leave spark on for 1 or 2 milliseconds prior to shutting the engine off, just so that we can burn off any additional junk that might be floating around in the cylinder. And it keeps the fuel injectors off until the engine goes back into the operating state. Now, the last thing to talk about with fuel injection is when we have a carbureted engine, we have to manipulate or restrict the airflow in when the engine is cold. You may have heard this term as a choke. What choking is it is restricting the amount of air to come in to basically richen up the fuel air mixture so that the engine remains running at colder temperatures. We also, too, because a carburetor is using engine vacuum to basically come off of fully closed of its needle and seat, and allow for the engine to run. We need to have the ability to be able to do that on fuel injection. So we're going to have an idle air control feature. And what this is going to allow for is this is going to allow for a metered amount of air to bypass the throttle valve and keep the engine running. This will allow for a more restricted passage when the engine is cold, so that we again can have a more richer fuel mixture and have the ability for the engine to stay running. But it can bypass around the throttle blade so that it does have enough air to run. When we're looking at how this is operated, typically the PCM or engine control unit is going to be controlling a stepper motor that is going to be actuated based off of the engine temperature and load. Obviously, we don't have to have the idle control bypass valve when the engine is accelerating, so it shuts off at that point. So we're only using it at idle And you will use the idle air control when we are at operating temperature as well, because it is allowing for the engine to maintain a consistent idle at all times. That covers the chapter 22 lecture. We will be getting into more detail about direct injected engines in chapter 23. That will be going into what kind of is more of the modern technology that we're going to have for fuel injection systems. But either way, I appreciate you sticking around to the end of the lecture, and I will see you in the next one.